And the lower right shows a controlled cooling process where we've gone through a controlled, software-controlled cooling of the plate to generate crystals as well. Each of these plates can be taken on. Here we're showing the same plates, and we're showing data from X-ray analysis. So each of these plates can be placed on an X-ray that has a translation stage. The X-ray will step through, collect the diffraction patterns from each one, and analyze. We then have another software package that allows us to compare the 2D and the XY traces of either the X-ray analysis or the XY results of a Raman analysis, and be able to do a cluster analysis so we can see where we have same and different types of results. This may not seem as significant when you're only doing 1 or 2 or 10 different analyses, but if you're doing several hundred analyses at a time, the only way to really compare results is to print things out and do a very laborious comparison of whether or not you're seeing peaks shift or new peaks appear. The software package we have allows one to handle very large numbers of samples quite conveniently, and allows scientists to look and review large sets of data and pick out which ones are the same and different, and be able to do form assignments based on those. We use the same package for, I'm showing an X-ray, and we use the same package for doing Raman as well. It also allows you to be able to quickly generate overlays so you can compare. In this particular case, the salt selection, we're able to generate a variety of different potential salt forms, each showing a unique X-ray, an X-ray trace. Out of that then, as I mentioned, we identify in this particular case, a number of potential salts that we can then scale up for stoichiometric analysis to see. And this is an example where we're looking at ephedrine. We were able to identify 8 ephedrine salts using one single set of experiments in really less than 2 weeks, using, in this particular case, a gram material. There have been cases where we've used much less than a gram material when we're just trying to do impact things at a very early stage. As you can see, when you do your analysis then, you can quantify the amount of counter ions present, whether it's the free base, like it is in the first example, whether you've got one equivalent of chloride or the mesylate, or you have a half equivalent of the phosphate. And in some cases, you can also characterize whether you've got another co-crystallite. In this particular case, we've got a water, so we're forming a hydrate in the case of the saltate. And the L-tartrate actually forms 2 forms. It forms an anhydrous form as well as a hydrate as well, a monohydrate. Finally, when we're doing this work, we actually generate a full report, a full physicochemical characterization of any of the forms that we actually find. We fully characterize each of the scaled-up forms with a series of analytics, X-ray, Raman, NMR, DFC, TGA, Carl Fisher, DDS, IC, and birefringence. We generate a full summary table as well as a full analysis of everything. And the software that we do really enables this. Most of our customers that actually take the equipment in-house do something similar, and they tie into their own particular set of analytics that they have, and they tie it into their own particular processes that they have as well. I have here a slide really seeking to talk to the impact that this workflow can have. Really, we see in our lab, and where the customers actually see, the ability to explore a wide range of conditions with a very limited amount of material very early in the process. So the intent here is to really enable a very broad exploration of many different potential crystallization conditions, both in terms of solvent composition, potential counter-ion, as well as different crystallization processes. And the second point here is really to reduce the time to market, and that's really shown down below. So down below, what we're trying to show is, the time frame, and really indicated in a series of days. So if materials come in and we kick off a study, the automated crystallization itself, in terms of setting up the robot and generating crystals, really it takes about a day. It takes about 24 hours to set things up. And in terms of people time, it just takes about an hour or 2 for the researcher's time to set up the actual equipment. The equipment itself then runs. It'll do all the creation of the samples. It'll do all the processing of the samples, all the filtration of the samples, and then all the various crystallization processes. So when the researcher comes in the next morning, the plates are ready to be dismantled, and solids isolated and passed on to the next series of analytics. So then the time scale here shows doing birefringence the following day, then Raman and X-ray perhaps. So really, if you started on a Monday, by the end of the week, you've got results out, you've done data sorting of your initial screening, so you can see where you're seeing initial potential different forms. We would then do scale-ups over the next week, allowing us to get detailed analysis out at the end of the next week. So really within 10 business days or 14 calendar days, we're able to turn around and generate full reports. And if you compare that to what is probably traditionally done, it can take a month or two, about 40 days of traditional methods to really go through. And if you're doing that, you are unlikely to really explore as fully the number of different crystallization conditions as well. I mentioned earlier that we have mentioned a couple of times we have a lab that does this work. We actually offer this as a service, as managed services to a number of different people. We do typical scope of study would be to do a 384 plate-based crystallization experiments. So consider 96 different compositions, each one with a slurry evaporation, a anti-solvent precipitation, and controlled cooling, with a variety of different analytics. Typically packaged with that up to 6 different scale-ups of each of those as well. We can handle any non-cytotoxic experimental compounds we study in our own labs. And from this, then, we would also do a variety of teleconferences and a full report. All these are capabilities we've also enabled with customers, so we've decided to bring in the equipment and the software. We've enabled this with a full training program and support as well. And so these are all things that we've done. We have people that have started with using our services to do a feasibility and prove the concept, to understand how the technology works. Some of these customers have then brought the equipment into their labs to enable their own research. And in some cases, we have examples where people have brought things into their labs. They continue to do the work, and occasionally they actually use our labs to either do additional capability or handle additional capacity that they may need. So this is actually the last slide I have, and then I can open up and take some questions. So really the idea is to really pull it all together and to use software and the informatics to really wrap around and enable not just the automation, but really to take advantage of the fact that in the area of crystallization, you want to rely on more than one piece of analytics. We aren't relying on just X-ray or just Raman or just birefringence, but really tying that all together. That can become quite cumbersome without the ability of really having an integrated workflow to pull all the data together, to generate it all, and be able to rapidly and easily generate reports to be able to make decisions. I think with that, I'd be happy to go back and answer questions and talk in detail about anything that people are interested in.
Okay, thanks, Eric. We've had a few questions come in the question and answer window, and I'll run through a few of them. For slide 18, if you could go back to that.
Certainly.
The question is, can we control the rate of evaporation here, control the formation of the desired state?
Right. It's a good question. So we don't control the rate directly. What we actually do is we have two ways to do sort of an indirect way of doing things. What we typically do is it's open to ambient, and we typically do a room temperature type of evaporation. We transfer material over and let things evaporate. In this particular case, most of the cases, this is used as an early screen, and we're looking for large differences between evaporation and some of the other processes, or precipitation or cooling or the slurry plate. In which case, it's so much different than other types of processes that it may not be important to control the rate of evaporation. Now, with that said, we have the ability of having different types of different types of openings at the top of the plate, so you can control the amount of mass transfer, the rate of evaporation that actually occurs. So there is some limited degree of control that is able to be there, but it isn't really control. It's mostly just doing a faster or a slower type of evaporation that can be done.